Okay, good morning, everyone. So last time we had started talking about angular momentum, which we defined to be this operator in 3 dimensions. We take the cross product of the position operator as a vector and the momentum operator as a vector, and we write the result as a vector. Oops. And I should say that this is actually orbital angular momentum. We're going to talk about more general angular momentum in a little bit. But L sub z here is equal to, we found, x times p sub y minus y times p sub x. And we said it doesn't matter what order we write those things in because x commutes with p sub y. And so given the fact that the order doesn't matter, it's also true that because the individual operators x and p sub y and p sub x are Hermitian, that means all 3 of L sub x, L sub y, and L sub z are also Hermitian operators. So this thing is a vector made out of Hermitian operators. And our next task is to see what this has to do with rotations. So let's consider a rotation. To make things simple, we will start with a rotation about the z-axis. Okay, and so our goal is to connect this to angular momentum in a little bit. So if we're rotating about the z-axis, we can just draw in the xy plane here. Let's say we're describing some point right there. And so there's a vector from the origin to that point, x, y, z. Okay, and we're going to rotate by some angle alpha. And so there's the new point after the rotation. This angle's alpha. And so geometrically, we can describe this by saying the coordinates x, y, and z are transformed into a rotation matrix, which is going to be cosine alpha minus sine alpha 0, sine alpha, cosine alpha 0, 0, 0, 1, acting on x, y, and z. Okay, or we can rewrite that as cosine alpha times x minus sine alpha times y, sine alpha times x plus cosine alpha times y, and then the z-coordinate is just left alone. So that's a general rotation by an angle alpha. And now we're going to take the special case that alpha is actually infinitesimal. So we're going to call it epsilon as a reminder that it's infinitesimal. And the good thing about that is then these trigonometric functions become simpler. So cosine of alpha is 1 minus epsilon squared over 2 plus epsilon to the 4th term. Sine alpha is approximately just epsilon plus an epsilon cubed term. And so if we're just working to first order in epsilon, all that's happening is x is being replaced by x minus epsilon times y. Y is being replaced by y plus epsilon times x. And of course, z has nothing happen to it. So what we'd like to do is define a operator that does this transformation. So consider an operator u of epsilon defined by the following. Okay, what we're going to do is we're going to define it so that when it acts on a state where the particle is known to be at some position, x, y, z, we get back the position after the rotation. So x minus epsilon y, y plus epsilon x, and z. Okay, so x, y, z, reminder, this is the state where the particle that we're describing is known to be at the point x, y, z. One way that we would know it was there is that we measured it. And x, y, and z are commuting observables, and therefore we can simultaneously measure them and find their eigenvalues. And that's the state. And so the operation of u of epsilon is to change this orthobasis state x, y, z into a different orthobasis state given by this. So the fact that we've done a change of basis, whenever you hear the word change of basis in quantum mechanics, that is supposed to tell you that there's a unitary operator that does the change of basis for you. Okay, so change of basis. We discussed this in general for transformations a while back. This is telling us that we have a unitary operator. Okay, and given this definition, this is the definition of the unitary operator. We can take its Hermitian conjugate. And so we can say that x, y, z, the bra, acted on by u epsilon dagger, is equal to, we're just going to take the Hermitian conjugate of the previous box. Okay, and now we're going to do a little trick. We're going to use the fact that this thing is a a unitary operator. So u of epsilon dagger is equal to the inverse of u by the definition of a unitary operator. And then if we look at how does the operator act here, we can see that to undo this, we would just take epsilon and replace it by minus epsilon. So the inverse of u, which is also the dagger of u, is the same thing as u of minus epsilon. So we're going to use that fact, and then we're going to take, in our previous equation, we're going to take epsilon and replace it by minus epsilon everywhere. So that tells us x, y, z, u of epsilon, because we took u epsilon dagger here, and we replaced it by u minus epsilon, and then we took epsilon goes to minus epsilon. That should equal the bra x plus epsilon y, y minus epsilon x, and z. Okay, and so now what we're going to do is we're going to take that equation and act on a ket that's describing the state of the system. X, y, and z here may or may not be describing the state of the system. This is just some basis vector. We may or may not be in an eigenstate of position, but we can now take this and act on the state of the system, which is some ket psi. Okay, and now because the bra xyz is on the left, this is something that we can translate into wave function language. In particular, this last expression here is the wave function evaluated at x plus epsilon y, y minus epsilon x, and z. Okay, and so what we can do with that is, because epsilon is infinitesimal, we can expand in a Taylor series. So this is the wave function psi xyz plus epsilon y, partial derivative with respect to x of psi of xyz, minus epsilon x, partial derivative with respect to y of psi of xyz. Okay, and then we can keep track of the fact that there are going to be order epsilon squared terms there too. Okay, so what we did here was Taylor series. Okay, and now we can use the fact that when you're in the position representation, we can relate these partial derivatives to operators. So in the position representation, a partial derivative with respect to x is represented or represents I over h bar times the operator p sub x. And similarly for the partial derivative with respect to y. Okay, and so what have we learned? We've learned that the matrix element xyz, u of epsilon, times an arbitrary state ket, psi, is equal to xyz. The identity operator minus I epsilon over h bar, I'm pulling out the constant factors. Okay, and then there is a factor of x here times this becomes a p sub y. Okay, and so this is x p sub y. And then the opposite thing happens here. This becomes the operator y, and then up to the factors of I h bar, this becomes a p sub x. So when I get all the minus signs in h bar straight, this is minus y p sub x here. Okay, and we're dropping order epsilon squared times psi. Okay, and the nice thing about this is I recognize this. We worked out that that was the z component of the angular momentum, L sub z. So if this equation is supposed to be true for any x, y, z and any psi, which it is because we didn't make any special assumptions about them, that tells us that the operator u of epsilon is equal to the identity operator minus I over h bar times epsilon L sub z. So all of that was for a infinitesimal epsilon, which we did because it's just easier to deal with infinitesimal numbers where we get to drop epsilon squared. But now we can take what we've learned and turn it into a statement about a finite angle. So for a finite angle alpha, the operator u of alpha is what you get when you just do this same thing for epsilon a large number of times. So we're going to take the limit as capital N goes to infinity of the identity minus I over h bar alpha over n times L sub z to the nth power. Okay, so notice alpha is actually equal to n times epsilon. Epsilon's very small, n is going to infinity in such a way that their product is this constant alpha. And then if we do epsilon, if we do the transformation by epsilon here, we have to do it n times in order to rotate by a full angle alpha. Okay, and then this is the very definition if you go back to when you first learned about exponentials, hopefully they taught it to you as this limit. This is the exponential of minus I over h bar alpha times L sub z. Okay, so one nice thing about this expression is this is indeed a unitary operator because we're taking the exponential of I times a Hermitian operator. Okay, so unitary, which we already knew it would have to be because e to the I times Hermitian. And at some point in the past, we proved that e to the I Hermitian operator is a unitary operator. Okay, so all of that was for rotations about the z-axis. And now for a rotation about a general axis, everything's going to be the same. Well, the derivation I just did will be a little more complicated, but the result will be the same. So let's call our general axis of rotation n hat. Okay, and then the unitary operator by an angle alpha in the n hat direction is going to be defined to be the exponential of minus I over h bar, the magnitude of alpha times n hat dotted into L, the angular momentum operator as a vector. Okay, so I'm assuming here this n hat is a unit vector. Okay, and so just to draw a picture, it's pointing in some arbitrary direction. And then we're doing a rotation about that direction by an angle alpha. When n hat is z hat, that's the case we did. So when n hat equals z hat, then n hat dot L is in fact L sub z, just like we had. Okay, but now what we've got here, therefore, is a formula that tells us how we can make an operator that does the unitary transformation, a unitary change of basis, to rotate about any angle by around any direction that we want. Okay, and it depends on the angle as a vector here, because the direction of it is telling us what axis we're rotating around, and the magnitude is telling us how far we're rotating. Okay, so when we derived this for the z direction, we used rectangular coordinates, but we could just as easily use cylindrical or spherical coordinates. So could also consider this same operator in cylindrical or spherical coordinates. And so the way we would do that is we'd write down position eigenkets, but instead of calling them x, y, z, we would call them r phi z if we're using cylindrical coordinates, or r theta phi if we're using spherical coordinates. Okay, and for what I'm about to do, it actually doesn't matter which one we use, because in either case, the relevant coordinate is going to be just phi. So to be specific, let's use spherical coordinates. So the way this would work is r theta phi times our unitary operator around the z-axis, acting on our state ket, the state that's the ket that describes the state we're in. That's equal to the wave function in spherical coordinates plus the epsilon part, which turns out to be just a derivative with respect to phi. So one way we know that it's actually just the derivative with respect to phi is if you write that in rectangular coordinates, that's y partial x minus x partial y, which is what we found in rectangular coordinates. Okay, and so then comparing to what we already did, this is telling us that the representation of the operator L sub z in this spherical coordinate position basis is, or cylindrical, is minus I h bar times the phi derivative. So that's nice and simple. That's actually going to make it easier to solve the eigenvalue problem. This is in the spherical coordinate position basis. So the reason it's easier, of course, is it just has one type of derivative in it. It doesn't have y and x derivatives and x and y derivatives like the rectangular coordinate does, which makes sense because we're dealing with a rotation. Rotations are going to be simpler in coordinates where one of the angles just corresponds to what you're rotating by. Okay, so let's solve this eigenvalue problem for this operator. Okay, for the eigenvalue problem is operator acting on an eigenket, which we're going to call L sub z, is equal to a number times the same ket. And so we want to solve simultaneously for the number L sub z and the ket that corresponds to it. Okay, and so the way we're going to do this is to use the spherical coordinate position basis by acting with the bra r theta phi on both sides. And when we do that, we're going to let r theta phi acting on the state L sub z, we're going to call that psi of phi. Okay, now it depends also on r and theta. So maybe technically we should write psi r of theta, but that would be sort of a waste of time because the only thing that's going to matter here is the dependence on phi, because that's what appears in the operator. And so I'm taking advantage of that to here only write it as a function of phi, even though secretly it also depends on r and theta. Okay, so now in the coordinate basis, or in the coordinate representation, okay, the acting of L sub z on this wave function is minus I h bar partial phi acting on psi of phi equals the eigenvalue L sub z acting on psi of phi. Okay, and so that's an equation that is not too hard to solve. The solution is that psi of phi is equal to a constant times e to the I eigenvalue L sub z times phi over h bar, right? So if you just plug that in to the previous differential equation, you can easily see that it works. So that's true up to normalization, which is the factor of c. Okay, and the range of phi is, remember, from 0 to 2 pi. So let's require this thing to be normalized. That says if we integrate over 0 to 2 pi of phi times psi of phi squared. But psi of phi squared here is just this constant c times a phase. And when we take the complex square, the phase goes to 1. So this is equal to, oops, this is equal to the magnitude of c squared. Okay, that's supposed to equal 1. Okay, and so c squared times 2 pi has to equal 1, which tells us that c is 1 over the square root of 2 pi times any arbitrary phase, and we're just going to choose that phase to be 1. Okay, so we know what the wave function the wave functions for the eigenkets of L sub z are. For them to be single valued, though, we have another requirement. For wave function to be single valued, what we need is that psi of phi should be equal to psi of phi plus 2 pi. In other words, if we rotate all the way around, we should get back to where we started. So that tells us c times e to the I L sub z phi over h bar should equal c e to the I L sub z phi over h bar times e to the I L z 2 pi over h bar. Okay, and so this factor must equal 1. And so what does that tell us? That tells us LZ 2 pi over h bar should equal a integer multiple of 2 pi. We'll call it m. Okay, which tells us that L sub z, our eigenvalue, must be h bar times an integer. Okay, so in both cases, this is m as an integer. And it's traditionally called m. The original reason for calling it m is because it's the magnetic quantum number. Oops. And the reason it's called the magnetic quantum number is because originally this became known when people did measurements of spectra involving magnetic fields, atoms and molecules in magnetic fields. And so that was, I think, even before it was understood that this had something to do with angular momentum. Okay, so what we've learned is that we can rewrite our eigenvalue equation as L sub z acting on a state which we're now going to call m, that's just a label telling us which state it is equal to h bar times m is an integer, times the same state, m. Okay, we're just rewriting, instead of labeling by L sub z, we've decided to label by m. Okay, now L sub z should be an observable. It's the angular momentum, it's part of the angular momentum, so hopefully that will be an observable. And for it to be an observable, the postulates of quantum mechanics say that it should be Hermitian. So let's just check and make sure it is. Check that L sub z is Hermitian. Okay, and so to do that, what I'm going to do is I'm going to take an arbitrary matrix element, psi2 L sub z psi1. That's an arbitrary matrix element of L sub z. And let's see what happens when we take its complex conjugate. Okay, so on the one hand, when we take its complex conjugate, that's equal to psi1 LZ dagger, psi2. Okay, and so that's definitely true. And then if L sub z is Hermitian, so I'll put a little question mark over this equal sign, that should be equal to psi1 LZ psi2. And so our job is to test whether this is actually true. And to test whether it's actually true, what we're going to do is do everything in the phi position representation. So let's first take the left-hand side. I'm going to write a big star inside parentheses for the left-hand side. So this matrix element is integral from 0 to 2 pi d phi of psi2 of phi star. And then the representation of L sub z is minus I h bar partial phi acting on psi1 of phi. Okay, and this is hopefully from the far right-hand side, this is equal to integral from 0 to 2 pi psi1 of phi star. That's coming from here. Okay, and then the L sub z acting on psi2 looks like this, minus I h bar partial phi psi2 of phi. So we're taking advantage of the fact that we know from way back up here, okay, we know how L sub z acts, oops, we know how it acts in the phi representation. It's minus I h bar times the phi derivative. Okay, so now let's work on the left-hand side here a little bit. Now everything is just ordinary functions and numbers, and so we can distribute the complex conjugate. And so when we take this complex conjugate of that one, they both go away. And so this left-hand side is equal to I h bar, minus I turned into I when I took the complex conjugate, integral 0 to 2 pi d phi, psi2 partial phi psi1 star. Now I've just decided to avoid clutter by taking off the phi as an argument. This is supposedly equal to, on the right-hand side, we have minus I h bar, integral 0 to 2 pi d phi of psi1 star partial phi psi2. So to see whether this is actually true, what we're going to do is take the integral on the right side and move it to the left. Okay, and now we have two integrals, both of them with an IH bar in front of them, so I can drop that factor. And so I'm asking the question of whether integral 0 to 2 pi of d phi of psi2 partial phi psi1 star plus psi1 star derivative of psi2. We're asking whether that's 0. If it is, then this will be then L sub z will be a Hermitian operator. And everything here in the square brackets I can rewrite as a total derivative. So that's a derivative of psi1 star psi2. Okay, and then the fundamental theorem of calculus says when I take the integral of a total derivative, I just get the function. So this says psi1 phi star psi2 of phi, first evaluated at phi equals 2 pi, then evaluated at phi equals 0. We're asking whether that's 0. And the answer is it will be if the wave functions are single valued. In other words, if when you go from 0 to 2 pi, the wave functions don't change. Okay, and so the answer is yes, L sub z is Hermitian. But notice this is related to the fact that our magnetic quantum number m is an integer, because that was also dependent on the fact that the wave functions were assumed to be single valued. Okay, now all of this was for orbital angular momentum. Things are going to be a little bit different when we do more general angular momenta, which we'll get to in a bit. Questions on any of that so far? Okay, so now that we have a Hermitian operator, which can be an observable, we can ask more general questions about it. So one thing we'd like to know is what the commutation relations are for angular momenta. And so recall from the last lecture that L sub x is y p sub z minus z p sub y. L sub y is z p sub x minus x p sub z. And L sub z is x p sub y minus y p sub x. And so now we can just go ahead and compute any commutators of any pair of those that we would like. So let's start with the commutator of L sub x and L sub y. Okay, so we can write that as the commutator y p sub z, z p sub x. Okay, there's going to be 4 terms because there's 2 terms in L sub x and 2 terms in L sub y. So the other terms are minus commutator z p sub y, z p sub x, minus commutator y p sub z, x p sub z, and then finally the commutator of z p sub y, x p sub z. Okay, so we have to compute all of those things, but some of them are easier than others. So for example, let's consider the second term here. Okay, the thing is, everything in it commutes with everything else, because z ignores p sub y and p sub x, and it certainly commutes with itself. P sub y ignores z and ignores that z, and it also commutes with p sub x. So everything here commutes with everything else, and so that whole thing is just 0. And the same exact thing happens to this term. Everything in it commutes with everything else. And so when I take the commutator, I can just pretend they're numbers, and ordinary numbers commute. So that's 0. That almost works on the first term, except the only thing that doesn't commute is this p sub z and that z. They don't commute, but everything else commutes with everything else. And so I can pull out the things that commute and just pretend they're numbers. This is y p sub x. And then the commutator part is p sub z with z, which is otherwise known as minus I h bar. And if I do the same thing with this term in the end, this is going to be x p sub y times the commutator of z with p sub z, which is otherwise known as plus I h bar. Okay, and so the whole thing is I h bar x p sub y minus y p sub x, which we recognize as L sub z. So this is I h bar L sub z.
Excuse me, Professor?
Yes.
So I got a little bit lost here. So from the LX, LY,
Mhm.
did you already have these calculations from before that you concluded with the right side, or is there a simple trick you did to it? I lost you for a moment.
So the commutator of any position operator with any momentum is IH bar. So for example
So
here,
the one before that,
which one?
yes. I mean, how you went directly from LX, LY to those YPZ, ZPX.
So
I understand you have those right there. I mean, yeah, how did you do it so fast?
I'm just plugging that in and that in. Okay, so there's YP sub Z with ZP sub X for that term. Okay, and then there's minus ZP sub Y with ZP sub X for this term. I'm just doing every pair that occurs in here. Okay, and then this
Oh,
is YP sub Z and minus XP sub Z. There's the minus sign. There's the XP sub Z. And then the last thing is minus and minus makes plus. And then there's ZP sub Y and there's XP sub Z. Okay?
okay. And then in the next step, you did the same thing to get from the YPZ ZPX to the YPXPZZ.
YPX.
Like that very first term and that last term.
Yeah, this term.
Yes.
Right. So then the argument is Y here commutes with everything else involved in the term. And so we can just pretend it's a number. And the same with P sub X. P sub X commutes with Z and P sub Z and Y. So the Y and the P sub X, we can pretend are numbers and just pull them out. And so all that's left is the P sub Z commute with Z.
So how did we know Y commutes with everything else?
So Y doesn't care anything about the coordinate Z or the coordinate X or its momentum. They're completely independent from each other. So
Okay.
that's right. So that's why we know that anything with just Y in it commutes with anything involving Z, right? Z or P sub Z.
Mm-hmm.
They just commute with each other. The only things that don't commute are Z with P sub Z, and that P sub Z commuted with Z is minus IH bar, and here it's plus IH bar because it's the other way around. Okay?
Okay.
All right, so we found Lx commuted with Ly is IH bar Lz, and then you can do similarly. The strategy is exactly the same, so I won't go over it. Ly with Lz is equal to IH bar Lx. And if I do the commutator of Lz with Lx, that's equal to IH bar Ly. Okay, so one can summarize this in the following way. If I take any particular component of L with any other particular component of L, okay, so here J and K are going to be X or Y or Z. This is equal to IH bar times a sum, n equals 1 to 3. Or, so X is 1, Y is 2, Z is 3 for this purpose. Okay, of epsilon JKN Ln, okay, where epsilon 1, 2, 3 is equal to epsilon 2, 3, 1 is equal to epsilon 3, 1, 2. Those are all 1. And epsilon 1, 3, 2 is equal to epsilon 3, 2, 1 is equal to epsilon 2, 1, 3 is equal to minus 1. And all others are 0. Okay, so this is the anti-symmetric tensor. And so this is just a way of summarizing all the different commutation relations for L's. Okay, so more generally, you could talk about any set of three operators that obey those commutation relations, and more generally, that is called an angular momentum. So more generally, an angular momentum, and it's traditional usually to write a general angular momentum as J. So it's a vector with three Hermitian components. Okay, each one of these is Hermitian. Okay, and it satisfies, this time I'm going to rewrite it not using the epsilon. I'm just going to write it as commutator Jx with Jy is equal to I h bar Jz. Jy with Jz is equal to I h bar Jx. And Jz with Jx is equal to I h bar Jy. So this is sometimes called the commutator algebra for angular momentum. So a commutator algebra is just some list of all the commutators relevant to some set of operators and telling you which ones are zero and which ones are non-zero, and in particular, what the commutators are equal to. Okay, so having done that, it's also useful to define the following thing because it's going to help us make a CSCO. We define J squared to be the sum of the squares of the individual ones, which is the vector magnitude squared. And this is also a Hermitian operator, so it's also eligible to be an observable. Okay, and so now we can compute it as part of the commutator algebra. We can compute the commutator of J squared with, let's say, Jx. Okay, so now let's do that. We'll split it up into parts. There's the part Jx squared with Jx, and the part Jy squared with Jx. Oops. And the part Jz squared with Jx. Okay, now the first term is clearly zero because anything commutes with itself. There's only one operator here, so it can just be a number for all we care. So let's work on the second term. So this is equal to Jy Jx minus Jx Jy. I'm just writing out the Jy squared. Okay, and now I can use commutation relations on these individual parts. For the first term, I can write this as Jy Jx Jy minus I h bar Jy Jz. Okay, so I used the commutation relation there. I'm also going to use it on the second term, including the minus sign, and write that as minus Jy Jx Jy minus I h bar Jz Jy. So I've used the commutation relation again. Okay, and the good thing about doing that is now this term cancels with that term. And so I'm left with minus I h bar Jy Jz plus Jz Jy. Okay, and then similarly, I can do the exact same strategy on the last term. I'll just write similarly here. This is equal to plus I h bar times what turns out to be the same exact thing. Okay, and so what we've learned is that the commutator j squared with jx is 0, which is good. That means they can be part of a complete set of commuting observables. Similarly, by the exact same strategy, I can do j squared with jy, that's 0. And same thing for z. There's nothing special about x versus y versus z. Okay, and this is actually the one that traditionally is used for a complete set of commuting observables. Right, we've got two operators there that are Hermitian, they're observables and they commute. Okay, but more generally, j squared commutes with the whole vector angular momentum operator to give 0. Okay, so next time we're going to take this general angular momentum operator, not worrying about whether or not it's orbital angular momentum or some other kind of angular momentum, which in fact it can be, and we're going to find the eigenvalues and eigenvectors of j squared and j sub z and j sub x and j sub y. So next time, the eigenvalue problem for j. All right, so that's it for today. And let me ask if there are any questions.
I have some questions from the text.
Okay.
I'll wait for others to ask first. Anyone else has questions?
Okay. Any other questions?
Okay, so Professor.
All right, let me stop the recording here.